Hello and welcome to Space Historians. I'm glad you've joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our world. This is your moment to leave the noise of the day behind and step quietly into the vast, starlit corridors of cosmic history. Tonight, we're wandering into one of the most astonishing frontiers humanity has ever explored. A place where time itself bends backward, where galaxies shine when they shouldn't exist, and where everything we thought we knew about the universe's beginning is being rewritten. If you enjoy these quiet journeys, a like and subscribe help keep this channel orbiting. But for now, you don't need to do anything but listen. There are moments in science when a single image changes everything, when what appears on a screen forces us to question decades of careful theory, when the impossible becomes undeniably real. The James Webb Space Telescope delivered such a moment not once, but repeatedly, sending back photographs of galaxies that by all rights should not exist. These were not just distant galaxies. They were ancient beyond measure, their light reaching us from a time when the universe itself was barely 400 million years old. To put that in perspective, if the universe's entire history were compressed into a single year, these galaxies appeared on January 2nd, in the earliest hours of cosmic dawn. According to every model we had built, every simulation we had run, every equation we trusted, those hours should have been dark. The universe should have been a fog of hydrogen gas, slowly cooling, slowly gathering, nowhere near ready to ignite into the brilliant structures we call galaxies. Yet there they were, shining impossibly bright in Webb's infrared vision, fully formed galaxies burning with billions of stars when our timeline said such things could not yet exist. The first astronomers to see these images felt something between wonder and vertigo. Here was light that had travelled for more than 13 billion years. Light that began its journey when space itself was still violently young. When the cosmic microwave background, that faint afterglow of the Big Bang, had only just released its grip on the darkness. This light should have shown us the universe's awkward infancy, small clumps of matter struggling to become stars, fragments slowly merging into the first tiny galaxies. Instead, it showed us galaxies that looked almost mature, galaxies with masses rivaling our own Milky Way, galaxies displaying order and structure that should have taken billions of years to develop. It was as though Webb had photographed a newborn baby and found it already grown, already walking, already speaking in full sentences. The shock rippled through the astronomical community within days. Press releases were carefully worded, hedging against premature conclusions, but behind closed doors, scientists were asking questions they had never expected to ask. Had the Big Bang happened earlier than we thought? Had galaxies formed faster than physics allowed? Or was there something fundamentally wrong with our understanding of cosmic time itself? What made this discovery even more unsettling was its consistency. These were not isolated anomalies, not flukes or measurement errors. Webb kept finding them, galaxy after galaxy, each one pushing against the boundaries of what the standard cosmological model predicted. Some contained stars that appeared chemically enriched, meaning earlier generations of stars had already lived and died, seeding space with heavy elements. Others showed organized disk structures, spiral arms, central bulges, the architectural features of mature galaxies that should have taken cosmic ages to assemble. The numbers told a story that refused to fit the script. Redshift measurements, the cosmic ruler that tells us how far back in time we are looking, confirmed these galaxies belonged to the universe's earliest epochs. Spectroscopy, the splitting of light into its component wavelengths, revealed their compositions and confirmed their ages. Every verification only deepened the mystery. This was not a case of misinterpretation or wishful thinking. The data were clear, precise, and reproducible. Webb, with its golden mirrors and infrared eyes, had pulled back a curtain on the early universe, and what lay behind that curtain contradicted the neat timeline humanity had spent a century constructing. The standard model of cosmology had always been our most successful framework, explaining the expansion of space, the formation of galaxies, the distribution of matter across billions of light years. It matched observations with extraordinary accuracy, from the cosmic microwave background to the abundance of hydrogen and helium forged in the Big Bang's first minutes. Scientists had grown comfortable with this model, confident that while details might need refinement, the broad strokes were correct. Shattered that confidence, not by proving the model wrong entirely, but by showing that something crucial was missing, something we had not accounted for in our equations, something that allowed the universe to leap ahead in complexity far sooner than we believed possible. As the weeks turned into months and more data poured in, the questions multiplied. Were we wrong about how stars form? Were we wrong about how galaxies grow? Were we wrong about the nature of dark matter, that invisible scaffolding upon which all structure depends? Or were we wrong about time itself, about the age of the universe, about the very sequence of events following the Big Bang? Each possibility opened new chasms of uncertainty, yet each also carried a spark of exhilaration. Because this is what science lives for, not the confirmation of comfortable ideas, but the collision with mystery, the moment when reality refuses to cooperate and demands we think deeper, look further, imagine beyond our current limits. Webb had not disproven the Big Bang. The evidence for that explosive beginning remained overwhelming, but it had shown us that our story of what came after, the slow, patient assembly of cosmic structure, was incomplete. And so we find ourselves at a threshold, standing between what we thought we knew and what we are only beginning to understand. The galaxies Webb revealed are not just objects of study. They are messengers from a time so remote, so inaccessible to ordinary experience, that their very existence feels like an impossible gift. They are windows into creation, into the moments when darkness first gave way to light, when the universe transitioned from formless energy into the structured beauty we see today. But they are also challenges, puzzles demanding answers, anomalies that will not be ignored. This is where our journey begins tonight, in that moment of impossible discovery, in the realization that the universe's earliest chapters were written in a script we cannot yet fully read, in the quiet understanding that everything we think we know about cosmic time may need to be revised. To understand what the James Webb Space Telescope found, we must first understand where it sits and why it was built to look the way it does. This is not just another telescope orbiting Earth like the Hubble before it. Webb floats in a place so remote, so carefully chosen, that it might as well exist in a realm apart from ordinary human experience. 1 million miles from Earth, roughly 4 times the distance to the Moon, Webb occupies a gravitational balance point called the second Lagrange point, a location where the combined pull of Earth and Sun creates a pocket of stability. Here, the telescope can orbit the Sun in lockstep with our planet, maintaining a fixed position relative to Earth while keeping its instruments perpetually cold, perpetually dark, perpetually focused on the deep universe. This distance was not arbitrary. It was essential. Webb's mission demanded conditions that low Earth orbit could never provide. The telescope's design tells the story of its purpose. Unlike Hubble, which sees in visible light the same wavelengths our eyes detect, Webb was built to see in infrared, wavelengths longer than red, invisible to human vision, but essential for penetrating the veils of dust and time that obscure the early universe. Every choice in its construction flowed from this singular goal to look farther back in time than any instrument before it, to capture light from galaxies born in the universe's first few 100 million years. At the heart of Webb sits a mirror unlike any other, composed of 18 hexagonal segments coated in gold, each one polished to near perfection, together spanning 6.5 meters across. Gold was chosen because it reflects infrared light with exceptional efficiency. The segmented design allowed the mirror to fold like origami during launch, fitting inside a rocket's narrow nose cone, then unfurling in space like a mechanical flower opening toward the stars. But the mirror alone would be useless without the sunshield, that enormous 5-layered structure, the size of a tennis court that protects Webb's instruments from the heat of the sun, Earth, and Moon. Each layer, thinner than a human hair, blocks infrared radiation, creating a temperature difference of hundreds of degrees between the hot side facing the sun and the cold side facing deep space. On that cold side, temperatures drop to nearly 40 Kelvin, just 40 degrees above absolute zero, cold enough that Webb's own warmth does not blind it to the faint infrared signals it seeks. This coldness is not optional, it is survival. Infrared light is essentially heat radiation. If Webb were warm, its own glow would drown out the ancient photons it was built to capture. So the telescope must stay frozen, its instruments operating at temperatures where nitrogen becomes liquid, where ordinary materials would shatter like glass. The journey to this frozen outpost began decades ago, not in space but in the minds of scientists who understood that Hubble, for all its brilliance, could only see so far. Visible light from the earliest galaxies has been stretched by the expansion of space, red shifted into infrared wavelengths that Hubble's instruments could barely detect. To truly peer into the cosmic dawn, humanity needed a telescope designed from the ground up to see what Hubble could not. Webb was that telescope, conceived in the 1990s, developed through the 2000s and 2010s, delayed repeatedly by technical challenges and budget overruns, nearly cancelled more than once, yet somehow surviving every crisis through the determination of thousands of engineers, scientists, and administrators who refused to let the dream die. Launch day came on December 25th, 2021, a Christmas morning when a European Ariane rocket lifted Webb from French Guiana and sent it arcing toward space. The 29 days that followed were among the most nerve-wracking in the history of space exploration. Webb had to execute more than 300 deployment steps, each one critical, each one unrehearsed in the weightlessness of space. The sunshield had to unfurl, tensioned by motors that had never operated beyond Earth. The mirror segments had to swing into position, aligning with nanometer precision. A single failure would have rendered the entire mission useless, and at 1,000,000 miles distance, no astronaut could fly out to repair it. Yet every step succeeded. The sunshield deployed perfectly. The mirrors aligned. The instruments came online, cooling to their operating temperatures, sending back test images that exceeded even optimistic expectations. When the first calibration photos appeared, showing stars so sharp they looked like jewels against velvet, scientists wept. Webb worked. After decades of waiting, it worked. But working was only the beginning. The telescope's true purpose lay not in perfect optics, but in what those optics could reveal. Webb's instruments were designed to dissect light, to split it into spectra showing the chemical fingerprints of distant objects, to measure red shifts with precision, to capture the faintest whispers of infrared radiation from galaxies so remote that their light began travelling before Earth existed. The setting was complete. A telescope hung in the frozen darkness 1,000,000 miles from home, staring endlessly into the abyss, waiting for ancient photons to arrive after journeys lasting billions of years. Scientists on Earth, linked by radio signals crossing that 1,000,000-mile gap, prepared to receive what Webb would send back, knowing that every image, every spectrum, every measurement could reshape humanity's understanding of cosmic history. And what Webb sent back exceeded every prediction, every hope, every fear. It showed galaxies where there should have been darkness. It showed structure where there should have been chaos. It showed maturity where there should have been infancy. The setting, That carefully engineered outpost in the cosmic cold had become the vantage point from which humanity would witness the impossible, the place from which we would see the universe as it truly was in its earliest moments, not as our theories predicted, but as nature had actually made it. From that frozen mirror a million miles away, the story of cosmic dawn was about to be rewritten. The first deep field images from Webb arrived in July of 2022, and with them came a revelation that would not stay quiet. Astronomers had pointed the telescope at a patch of sky so small it could be covered by a grain of sand held at arm's length, the same approach Hubble had used decades earlier to reveal thousands of previously unseen galaxies. Webb's version of this cosmic census was expected to show similar wonders, perhaps with greater clarity, perhaps reaching slightly farther back in time. What it actually revealed was something no one had fully prepared for. The image showed galaxies, thousands of them, scattered like luminous seeds across the darkness. But as astronomers began analyzing the light from these objects, measuring their red shifts and calculating their distances, a pattern emerged that defied comfortable explanation. Many of these galaxies were extraordinarily distant. Their light stretched so severely by cosmic expansion that it had shifted from visible wavelengths deep into the infrared. This meant they were old, not in the sense of having existed for a long time, but in the sense of existing long ago, when the universe itself was young. Some of these galaxies showed redshift values exceeding 10, meaning their light had been travelling for more than 13 billion years, arriving now from an epoch when the universe was less than 500 million years old. At those distances, at those times, the standard cosmological timeline predicted only small, irregular proto-galaxies, fragments still gathering mass, still learning how to become the structured systems we recognize today. Yet Webb showed galaxies that were neither small nor irregular. They were massive, containing billions of stars, displaying organized structures, shining with a brightness that suggested vigorous star formation, or perhaps even mature stellar populations. They looked like galaxies that belonged to a much later era, galaxies that should not have had time to assemble in the brief window since the Big Bang. The discovery was not a single anomaly, but a recurring theme. As Webb continued its surveys, peering into different regions of the sky, it kept finding these impossibly early galaxies. Each new detection reinforced the pattern. The early universe was not empty, not chaotic, not slowly fumbling toward complexity. It was already alive with structure, already burning with starlight, already displaying the kind of organization that theories said required billions of years to develop. Scientists began checking and rechecking their calculations. Redshift measurements were confirmed spectroscopically, eliminating the possibility that these were nearby galaxies masquerading as distant ones. Photometric data from multiple filters supported the conclusions. Computer models were run and rerun, testing whether different assumptions about star formation or dust content could explain the observations. The results held. These galaxies were genuinely ancient, genuinely massive, and genuinely problematic for the standard timeline. What made the discovery even more striking was the diversity among these early galaxies. Some appeared blue in Webb's infrared vision, suggesting they were filled with young, hot stars still in the midst of formation. Others showed redder colours, hinting at older stellar populations. Stars that had already passed through their youth and settled into longer-lived phases. The presence of old stars in galaxies existing less than 500 million years after the Big Bang raised immediate questions. If those stars were old, they must have formed even earlier, pushing the timeline of stellar birth back into epochs that were supposed to be dominated by darkness. The light Webb captured was older than stars should have been, older than galaxies should have been, older than the neat progression from simplicity to complexity that cosmology had long assumed. It was light from a time we thought we understood but clearly did not. Light that carried messages written in a language we were only beginning to decipher. Among the most puzzling aspects was the sheer number of these galaxies. Early predictions had suggested that massive galaxies in the first billion years would be rare, perhaps non-existent. Webb was finding them in abundance, far more than models predicted. If the early universe could produce so many large galaxies so quickly, then something about our understanding of galaxy formation efficiency, of gas cooling rates, of dark matter clustering had to be revised. Some galaxies showed evidence of chemical enrichment, the presence of elements heavier than hydrogen and helium, elements that could only be forged in the nuclear furnaces of stars. This meant that at least one generation of stars had already lived and died, spreading their ashes into the gas that formed the next generation. The speed of this cycle, from primordial hydrogen to enriched stellar populations, seemed impossibly fast. Stars need time to form, time to burn through their fuel, time to explode or collapse. Yet here was evidence that all of this had already happened within the universe's first few 100 million years. The discovery forced a reckoning. For decades, cosmologists had constructed a timeline based on careful observations of the cosmic microwave background, the distribution of galaxies in the nearby universe, and simulations of how structure grows under gravity's patient pull. That timeline was elegant, consistent, and supported by mountains of data. Webb had not disproven it, but it had revealed cracks, places where the observations no longer matched the predictions, places where reality leapt ahead of theory. The light older than stars became a phrase whispered among astronomers, a shorthand for the mystery Webb had unveiled. It captured both the wonder and the confusion. The realization that photons arriving now from the edge of the observable universe carried stories that contradicted the narratives we had written for them. This was not the first time a telescope had surprised us. Hubble itself had reshaped cosmology, revealing an accelerating universe powered by dark energy, a discovery that earned a Nobel Prize and forced physicists to rethink the fabric of space. But Webb's surprises felt different, more fundamental. They struck at the very sequence of cosmic events, at the timeline itself, at the question of when things happened and how fast the universe could move from formless void to structured brilliance. The discovery of light older than stars was just the beginning, the opening note in a symphony of anomalies that would challenge everything we thought we knew about the universe's earliest chapters. When the first results from Webb began circulating through the astronomical community, the initial reaction was not celebration but skepticism. Scientists are trained to doubt, to question, to demand extraordinary evidence for extraordinary claims. And the claims emerging from Webb's deep fields were nothing if not extraordinary. Galaxies existing when they should not, massive structures appearing impossibly early, a cosmic timeline that seemed compressed beyond recognition. These were not minor adjustments to existing models, but fundamental challenges. In conference rooms and virtual meetings, researchers pored over the data with critical eyes. Some questioned the redshift measurements, wondering if there might be alternative explanations for the observed wavelengths. Could dust be reddening the light of closer galaxies, making them appear more distant than they actually were? Could unusual emission lines from exotic objects be mimicking the signatures of high redshift galaxies? These were not frivolous objections, but necessary caution, the scientific method demanding that all alternatives be explored before accepting a revolutionary conclusion. Others focused on the mass estimates. Calculating a galaxy's mass from its light requires assumptions about the types of stars it contains, about how efficiently those stars convert gas into stellar matter, about the ratio of visible to dark matter in the early universe. If any of those assumptions were wrong, the derived masses could be overestimated, making these galaxies seem more impressive than they truly were. Teams ran different models, testing various star formation histories. adjusting parameters to see if the anomalies might disappear. They did not. The disbelief was not rooted in stubbornness, but in experience. Astronomy has a history of false alarms, of exciting discoveries that evaporated under closer scrutiny. Pulsars were once thought to be signals from alien civilizations. Faster-than-light neutrinos turned out to be loose cables. Scientists had learned the hard way that the universe can be deceptive, that what looks like a revolution might simply be a misunderstanding. Webb's galaxies demanded the same rigorous skepticism. Yet, as weeks turned into months and more observations accumulated, the skepticism began to soften. Spectroscopic follow-up confirmed many of the early redshift estimates. Galaxies that appeared distant in initial photometric surveys proved genuinely distant when their light was split into detailed spectra. The chemical fingerprints were unmistakable, the stretching of spectral lines consistent with light that had travelled across more than 13 billion years of expanding space. Teams working independently, using different methods and different telescopes, began reaching similar conclusions. The early massive galaxies were real. They were not measurement errors or flukes. They represented a genuine phenomenon that demanded explanation. The tone of scientific discourse shifted. Early papers had used cautious language, hedging their conclusions with phrases like possibly, or potentially, or if confirmed. Later papers grew bolder, stating plainly that the observations conflicted with standard models, that revisions would be necessary, that something fundamental about our understanding of the early universe needed to change. But disbelief lingered in certain quarters. Some senior astronomers, veterans of earlier controversies, urged restraint. They pointed out that Webb was still new, that calibration issues might yet be discovered, that the field needed time to fully understand the telescope's capabilities, limitations. They warned against premature announcements, against headlines proclaiming the Big Bang was wrong or cosmology was in crisis, knowing how easily nuance could be lost in translation from scientific journals to public media. This tension between excitement and caution played out in real time across social media, at conferences, in journal clubs, where researchers gathered to dissect the latest findings. Younger scientists, less invested in existing models, tended toward enthusiasm, seeing Webb's anomalies as opportunities for discovery, chances to make their mark by solving puzzles their predecessors could not. Older scientists, having witnessed paradigm shifts before, approached the data with measured deliberation, insisting on reproducibility, on cross-checks, on the slow accumulation of evidence that builds consensus. The human element was palpable. These were not abstract debates, but passionate arguments among people who had devoted their lives to understanding the cosmos. For some, Webb's discoveries were validations of long-held suspicions that the standard model was incomplete. For others, they were threats to frameworks they had helped build, theories they had tested and refined over decades. The emotional stakes were high, even as the scientific standards remained rigorous. Disbelief also manifested in creative theorizing. Rather than accepting that the timeline was wrong, some researchers proposed modifications that might save the standard model. Perhaps star formation in the early universe was far more efficient than assumed, converting gas into stars at rates approaching theoretical limits. Perhaps the initial seeds from inflation were larger than expected, giving structure a head start. Perhaps feedback processes that regulate star formation today were weaker back then, allowing galaxies to grow unchecked. Each proposal was a way of preserving the core framework while accommodating the anomalies, a scientific version of the 5 stages, of grief where denial gives way to bargaining before acceptance arrives. The community was collectively working through shock, testing whether the impossible might somehow be explained within familiar bounds, before admitting that familiar bounds might need expanding. What made this period particularly fascinating was its transparency. Unlike earlier eras when discoveries might remain confined to specialist circles for years, Webb's findings spread rapidly through preprint servers and open access journals. Anyone with internet access could read the latest papers, see the data, follow the arguments. The scientific process was unfolding in public view, with all its uncertainty and debate visible to anyone interested enough to watch. The first response to Webb's discoveries was thus a mixture of wonder and wariness, of excitement tempered by caution, of minds simultaneously opening to new possibilities and clinging to established certainties. It was science at its most human, revealing not just the process of discovery but the emotions that accompany it, the disbelief that eventually yields to evidence, the slow transformation from skepticism to acknowledgement that something genuinely new has entered our understanding. And through it all, Webb kept observing, keep sending data, keep accumulating evidence that would make disbelief increasingly difficult to sustain. At the heart of modern cosmology lies a timeline, a carefully constructed sequence of events beginning with the Big Bang and unfolding across nearly 14 billion years. This timeline is not guesswork but the product of decades of observation, measurement, and theoretical refinement. It tells us when atoms first formed, when stars ignited, when galaxies assembled, when the universe transitioned from opacity to transparency. Every major discovery in 20th century astronomy helped build this timeline, and by the early 21st century it seemed remarkably solid. Then Webb looked back and found galaxies that did not fit. The contradiction is not subtle. According to the standard timeline, the first few 100 million years after the Big Bang should have been a period of slow assembly. Gravity would pull together small clumps of dark matter. Ordinary matter, mostly hydrogen and helium gas, would fall into those gravitational wells. The gas would cool and condense, eventually becoming dense enough to ignite the first stars. Those stars would gather into small groups, proto-galaxies containing perhaps millions of stars rather than billions. Over time, these fragments would merge, growing larger through countless collisions, until after 1 billion years or more, recognizable galaxies would emerge. This was the hierarchical model of structure formation, built from the bottom up, small things combining into larger things in a gradual cosmic construction project. The cosmic microwave background supported this picture, showing tiny density fluctuations that would serve as seeds. Computer simulations ran the clock forward from those seeds and produced galaxies that looked reasonably similar to what we observe in the nearby universe. Webb showed galaxies at redshifts corresponding to ages of 400, 500, 600 million years. Galaxies that should have been in those early fragmentary stages. Instead, they appeared massive and mature. Some contained as many stars as the Milky Way, which itself took billions of years to reach its current size. Others displayed organized structures, disks and bulges that indicated settled dynamics rather than chaotic youth. Still others showed evidence of multiple generations of stars, meaning the cycle of birth, death, and rebirth had already completed at least once. The timeline could not accommodate this. There simply was not enough time between the Big Bang and these observations for galaxies to grow so large through the standard processes. Even if star formation happened at maximum efficiency, even if every available gas cloud converted to stars as quickly as physics allowed, even if mergers happened continuously, the numbers did not add up. The galaxies Webb saw were too big, too fast. This created a logical contradiction. If the observations were correct, and mounting evidence suggested they were, then either the processes worked differently than we thought, or the timeline itself was wrong. Perhaps the universe was older than 13.8 billion years, giving galaxies more time to form. Perhaps dark matter clumped earlier than models predicted, providing deeper gravitational wells that accelerated assembly. Perhaps some unknown mechanism seeded large structures directly, bypassing the bottom-up hierarchy entirely. Each possibility opened new questions. An older universe would solve the time problem, but would conflict with precise measurements of the cosmic microwave background and the expansion rate. Faster dark matter clustering would require modifications to the properties of dark matter itself, properties constrained by other observations. Direct seeding of large structures would demand new physics, some process operating in the early universe that we had not yet identified. The contradiction also extended to stellar populations. Stars have lifetimes determined by their mass. Massive stars burn hot and die young, living only a few million years before exploding as supernovae. Smaller stars burn slowly, potentially lasting billions of years. If Webb's early galaxies contained old stars showing redder colours and chemical enrichment, then those stars must have formed even earlier, perhaps just 100 or 200 million years after the Big Bang. But the universe at 100 or 200 million years old should have been in its dark ages, the period after the cosmic microwave background was released, but before the first stars ignited. Finding evidence that stars existed during or immediately after this period meant the dark ages were shorter than expected, perhaps even non-existent in some regions. The timeline that carefully separated epochs, one following the other in orderly succession, was being compressed and overlapped. Some scientists proposed that the contradiction might be resolved through measurement uncertainties. Perhaps the masses of these galaxies were overestimated. Perhaps their light was being magnified by gravitational lensing, making them appear brighter and more massive than they truly were. Perhaps the star formation histories were different from assumed, with brief intense bursts creating the appearance of large stellar masses without actually requiring as much time. These explanations were tested and found wanting. Lensing could account for some objects, but not the broad population of early massive galaxies. Different star formation histories helped, but could not fully close the gap. The measurements became more refined, the uncertainties shrank, and the contradiction remained. Breaking the timeline was not something astronomers took lightly. That timeline represented a century of progress, from Hubble's discovery of cosmic expansion to the detection of the microwave background to the precision cosmology of satellite missions like Planck. It had survived countless tests and predicted phenomena that were later confirmed. To suggest it needed major revision was to challenge one of science's great success stories. Yet Webb was doing exactly that, not through theoretical argument but through direct observation. The telescope was showing us the universe as it actually was at early times, and that universe looked different from what the timeline predicted. The contradiction was undeniable. Either our models of how galaxies form were incomplete, or our understanding of when they formed was wrong, or both. This was the nature of the crisis Webb had created. Not a failure of science, but a success. The discovery of a genuine puzzle that could not be dismissed or explained away. The timeline humanity had built to describe the universe's history was breaking under the weight of evidence, and in that breaking lay the promise of deeper understanding. When confronted with observations that defy explanation, scientists do what they have always done. They theorize, they debate, they divide into camps, each proposing different solutions to the same puzzle. Webb's discoveries of impossibly early galaxies triggered exactly this response, fracturing the astronomical community into competing schools of thought, each convinced their approach held the key to resolving the contradictions. The first group insisted the standard model could be saved with minor adjustments. These were the conservatives, not in a political sense but in their approach to scientific change. They argued that galaxy formation might simply be more efficient in the early universe than current models assumed. Perhaps gas cooled faster, perhaps star formation proceeded without the delays and interruptions we observe in nearby galaxies. Perhaps the feedback mechanisms that slow growth today Stellar winds, supernova explosions, radiation pressure were weaker back then. With the right tweaks to parameters, they suggested, simulations might reproduce Webb's observations without abandoning the fundamental framework. This camp found support in the details. When researchers adjusted their models to allow for higher star formation efficiency or reduced feedback, some of Webb's galaxies could be explained. Not all of them, but enough to suggest the approach had merit. These scientists published papers showing that with optimized conditions, galaxies could grow faster than previously thought, reaching substantial masses within the tight timeline the standard cosmology allowed. But their critics pointed out the problem with optimization. If you adjust enough parameters, you can fit almost any observation, but at some point, the adjustments become contrived, losing predictive power. Science demands not just that models fit existing data, but that they make testable predictions about future observations. If the standard model required extensive fine-tuning to match Webb's findings, perhaps it was telling us something more fundamental needed changing. The second group proposed modifications to dark matter. In the standard picture, dark matter is cold, meaning its particles move slowly enough that they clump into structures of all sizes. But what if dark matter was warm, with particles moving faster? Or what if dark matter interacted with itself in ways we had not considered? These variations could alter how and when structures formed, potentially explaining why galaxies appeared earlier and larger than cold dark matter alone would predict. Warm dark matter simulations showed promise. By suppressing the formation of very small halos while enhancing slightly larger ones, they could shift the galaxy formation timeline, making massive galaxies appear sooner. Self-interacting dark matter produced different halo shapes and densities, potentially affecting how efficiently gas could cool and form stars. Both ideas had been explored before Webb's discoveries, but now they gained renewed attention as possible solutions to the early galaxy problem. The challenge for this camp was consistency. Dark matter's properties are constrained by many observations beyond galaxy formation, from the cosmic microwave background to gravitational lensing to the distribution of galaxy clusters. Any modification that solved Webb's puzzle had to avoid breaking what already worked elsewhere. Threading that needle proved difficult, and debates raged over whether the same dark matter model that explained early galaxies could still explain everything else. A third group looked to the Big Bang itself, suggesting that the initial conditions might have been different from standard assumptions. Perhaps the density fluctuations imprinted during inflation were larger or more varied than the cosmic microwave background indicated. Perhaps there were rare peaks in the density field, regions where matter was concentrated enough to form galaxies exceptionally early. Webb might be selectively finding these rare regions, giving us a biased view of the early universe. This statistical argument had appeal. If most of the early universe matched predictions, but a few special locations formed galaxies quickly, then Webb, by targeting the most distant detectable objects, would naturally find the exceptions rather than the rule. The theory preserved the standard model for most of the cosmos, while allowing for unusual outliers. Critics countered that Webb was finding too many early galaxies for them all to be rare outliers. The statistics did not support the idea that these were exceptional regions. They seemed too common, suggesting something systematic rather than statistical was at play. Then there were the radicals, scientists willing to question deeper assumptions. Some proposed that the universe might be older than 13.8 billion years, that errors in measuring the expansion rate or the microwave background could have led to an underestimate. An older universe would give galaxies more time, potentially resolving the contradiction. Others suggested that our understanding of redshift might be incomplete, that distance and time relationships in the early universe could differ from what we calculate using standard cosmology. A few even floated ideas about cyclic universes, or bounces, where the Big Bang was not an absolute beginning, but a transition from a previous state. If structures could be seeded from before the bounce, galaxies might form faster than a fresh start would allow. These ideas lived at the fringe, speculative and difficult to test, but Webb's anomalies gave them new life. The division among theories was not hostile but productive, each camp pushing the others to sharpen arguments, to find better evidence, to test predictions. Conferences became arenas for debate, papers responded to papers, and gradually a consensus began to form, not around a single answer, but around the recognition that multiple factors might be at play. Perhaps star formation was more efficient and dark matter behaved slightly differently, and the initial conditions had more variation than expected. Perhaps the solution was not one clean explanation, but a combination of adjustments, each addressing part of the puzzle. What united all these theories was the acknowledgement that Webb had genuinely challenged cosmology. This was not business as usual, not a matter of filling in details. This was a moment when the frontier of knowledge had shifted, when established ideas faced serious pressure, when the scientific community had to confront the possibility that something fundamental about our cosmic story needed rewriting. The theories would continue to divide and evolve as more data arrived. But already, conversation had changed, moving from whether there was a problem to what kind of problem it was and how best to solve it. Science does not accept mysteries passively. When confronted with anomalies, it investigates, systematically gathering evidence, testing hypotheses, probing deeper until the unknown begins to yield. Webb's early galaxies demanded exactly this kind of pursuit, and astronomers around the world launched into an intensive investigation, using every tool at their disposal to understand what they were seeing. The investigation centered on spectroscopy, the technique of splitting light into its component wavelengths to reveal the physical properties of distant objects. While Webb's initial discoveries came from broad surveys using photometry, measuring brightness in different filters, spectroscopy provided the confirmation and detail those surveys lacked. By capturing the spectra of individual galaxies, astronomers could measure precise redshifts, determine chemical compositions, estimate stellar ages, and assess star formation rates. Webb's spectrographs, instruments designed specifically for this task, began targeting the most promising candidates. Light from distant galaxies was collected by the telescope's mirror, focused into narrow slits, then dispersed by gratings that spread each wavelength across detectors like a rainbow. The resulting spectra showed dark absorption lines where elements in the galaxy absorbed specific colors, and bright emission lines where gas clouds glowed with characteristic wavelengths. These spectral features were the key to unlocking the galaxy's secrets. By measuring how far the lines had shifted toward redder wavelengths, astronomers could calculate exactly how much the universe had expanded since the light was emitted, translating that expansion into a look-back time. A line normally appearing in the ultraviolet might show up in the near-infrared, stretched by a factor of 10 or more, indicating the galaxy existed when the universe was less than 5% of its current age. But spectroscopy revealed more than just distance. The strength and shape of emission lines told astronomers about the gas within these galaxies, about its temperature, its density, its ionization state. Strong oxygen lines indicated that heavy elements were already present, forged in earlier generations of stars and dispersed through supernova explosions. Hydrogen lines revealed ongoing star formation, regions where new stars were igniting from collapsing gas clouds. The relative strengths of different elements provided clues about the stellar populations, about whether the stars were young and hot or older and cooler. As spectra accumulated, patterns emerged. Many of Webb's early galaxies showed evidence of active star formation, their spectra dominated by the signatures of hot young stars pouring ultraviolet light into surrounding gas. Others displayed quieter profiles, suggesting they had already passed, through intense bursts, and were settling into more sedate phases. Still others showed complex spectra indicating multiple episodes of formation, waves of starbirth separated by quieter intervals. The investigation also included careful studies of morphology, the shapes and structures of these galaxies. While distant galaxies appeared as mere smudges even to Webb, image processing techniques could extract information about their sizes, their light distributions, whether they were compact or extended, whether they showed signs of disks or irregular clumps. Some early galaxies proved surprisingly small and compact, packing tremendous masses into regions just a few thousand light-years across. Others were more extended, approaching the sizes of modern galaxies despite their youth. Gravitational lensing became another investigative tool. Massive galaxy clusters can bend and magnify the light from more distant galaxies behind them, acting as natural telescopes. Webb targeted several of these cosmic lenses, capturing detailed views of galaxies so distant and faint they would be invisible without the magnification. These lensed galaxies provided unique opportunities to study early structures in unprecedented detail, revealing clumps, streams, and features invisible in unlensed objects. Collaboration amplified the investigation's power. Teams across continents shared data, compared results, and cross-checked measurements. A spectrum taken by one group would be verified by another using different methods. Photometric redshifts would be confirmed spectroscopically. Models developed in one research center would be tested against observations from another. This collective effort meant that errors could be caught quickly, that biases could be identified, that the conclusions would rest on a foundation broader than any single team could provide. The investigation was not without challenges. Observing time on Webb was precious, allocated through competitive proposals where demand far exceeded supply. Teams had to argue for their targets, demonstrating that their galaxies were worth the hours of telescope time required for deep spectroscopy. Technical difficulties arose as well. Some galaxies were so faint that obtaining high-quality spectra required many hours of integration, pushing the telescope to its limits. Cosmic rays struck detectors, creating spurious signals that had to be carefully removed. Calibration uncertainties had to be understood and minimized. Yet despite these challenges, the investigation progressed rapidly. Within months of Webb's first observations, dozens of early galaxies had been spectroscopically confirmed. Their red shifts matched or exceeded initial estimates. Their properties, while sometimes surprising, were reproducible across independent measurements. The anomalies were real, verified by multiple teams using rigorous methods. The pursuit of answers also drove theoretical investigations. Astrophysicists ran new simulations, testing whether modified star formation recipes or different dark matter models could reproduce Webb's observations. They explored parameter space, adjusting assumptions about gas physics, supernova feedback, black hole growth, looking for combinations that might explain the data. Some simulations came close, matching certain aspects of the observations while failing on others. None provided a complete explanation. As the investigation deepened, the scope expanded. Astronomers began searching for even more distant galaxies, pushing Webb toward its theoretical limits, seeking objects at red shifts of 15 or 20, epochs when the universe was barely 100 million years old. Early candidates were identified, though confirmation remained challenging. If galaxies existed at such extreme distances, the timeline crisis would only intensify. The investigation also turned toward complementary observations. Other telescopes, ground-based facilities, and space missions alike contributed data at different wavelengths. Radio observations probed cold gas reservoirs. X-ray satellites looked for active black holes. Combining these multi-wavelength views built a more complete picture of what these early galaxies were and how they formed. Through it all, the central mystery remained. Webb kept finding galaxies that should not exist, and the investigation kept confirming they were real. Behind every image, every headline, every moment of wonder lies data, the raw material of scientific understanding. Numbers, measurements, values recorded with precision and analysed with care. For Webb's discoveries, the data are not vague impressions but concrete evidence, quantities that can be verified, reproduced, and scrutinised. Understanding what Webb found means understanding what the numbers actually tell us. The most fundamental measurement is redshift, expressed as a value called Z. A galaxy at redshift 0 is in our immediate neighbourhood, its light unstretched by cosmic expansion. A galaxy at redshift 1 has had its light stretched by a factor of 2, meaning the universe has doubled in size since that light was emitted. Webb's early galaxies show redshifts ranging from 7 to 14 or higher, meaning their light has been stretched by factors of 8 to 15 times, travelling across more than 13 billion years of expanding space. These are not estimates but measurements derived from spectra. When astronomers identify emission lines in a galaxy's spectrum, they can compare the observed wavelength with the known rest wavelength, the colour that line would have in a laboratory on Earth. The ratio between these wavelengths gives the redshift directly. For a galaxy at redshift 10, a spectral line normally appearing at 400 nanometers in the ultraviolet will show up at 4,400 nanometers in the infrared, shifted by a factor of 11. The precision of these measurements varies. Photometric redshifts, estimated from brightness in multiple filters, typically have uncertainties of 10 to 20%. Spectroscopic redshifts, measured from detailed spectra, can be accurate to a fraction of a percent. As Webb's observations progressed, more galaxies received spectroscopic confirmation, turning tentative candidates into solid detections. Mass is another critical measurement. Astronomers estimate galaxy masses by measuring their brightness and assuming a relationship between light and stellar mass. A galaxy shining with a certain luminosity in infrared light likely contains a corresponding mass of stars. The exact conversion depends on assumptions about stellar populations, about the mix of hot young stars versus cool old ones, about how much dust might be absorbing and re-emitting light. Different models give different answers, but the range is typically not large enough to change the fundamental conclusion. Webb's early galaxies contain tens of billions to hundreds of billions of solar masses, comparable to or exceeding the Milky Way's stellar mass. Star formation rates provide another window into these galaxies' behavior. Emission lines from ionized gas, particularly hydrogen and oxygen, reveal where new stars are being born. The strength of these lines correlates with the rate at which gas is collapsing into stars. Webb's early galaxies show star formation rates ranging from a few solar masses per year to hundreds of solar masses per year. For comparison, the Milky Way currently forms about 2 solar masses worth of stars annually. These early systems were building stars at rates 10 to 100 times faster. Chemical composition emerges from spectral analysis. The presence of oxygen, carbon, nitrogen, and other heavy elements indicates that multiple generations of stars have already lived and died. Measuring the relative abundances of these elements tells astronomers about the stellar population's ages and histories. Some of Webb's early galaxies show oxygen abundances approaching 10 to 20% of solar values, surprisingly high for objects existing so early when the universe should have been chemically pristine. Sizes come from measuring how light is distributed across each galaxy's image. Even though these galaxies appear as tiny smudges, careful analysis can determine whether they are compact, with light concentrated in a small region, or extended, spread across larger areas. Webb's early massive galaxies tend to be compact, with effective radii of just 1 to 2,000 light-years, much smaller than modern galaxies of similar mass. This compactness implies high stellar densities. environments where stars are packed much closer together than in our own galactic neighborhood. Ages are perhaps the trickiest measurement. Astronomers cannot directly measure how long a galaxy has been forming stars, but they can infer ages from spectral features. The colors of a galaxy, particularly the balance between blue and red light, indicate whether its stars are predominantly young or old. By fitting models of stellar evolution to observed spectra, astronomers can estimate the average age of a galaxy's stars. For some of Webb's early galaxies, these fits suggest stellar populations several 100 million years old, which is problematic when the universe itself was only 400 to 500 million years old, leaving little time for those stars to have formed and aged. Dust content affects many of these measurements. Dust grains, tiny particles of carbon and silicon forged in stellar atmospheres, absorb ultraviolet and visible light and re-emit it in the infrared. Galaxies with significant dust can appear redder and dimmer than they would otherwise, potentially biasing mass and age estimates. Webb's infrared sensitivity helps mitigate this by seeing through some of the dust, but uncertainties remain. Some researchers argue that accounting for dust could reduce the inferred masses of early galaxies, easing the tension with models. Others point out that if these galaxies contain substantial dust, that itself is surprising, since dust requires heavy elements from previous stellar generations. The data also include upper limits, measurements of what Webb did not find. Searches for galaxies at even higher redshifts, beyond 15 or 16, have so far yielded few confirmed detections. This might indicate a genuine edge to galaxy formation, a point beyond which conditions were too harsh for structures to assemble. Or it might simply reflect the limits of Webb's sensitivity, the faintest galaxies remaining beyond reach, even for this powerful telescope. Error bars accompany every measurement, quantifying uncertainties. When astronomers report a galaxy's mass, they include a range reflecting possible variations in assumptions and measurement noise. When they report a redshift, they note the confidence level. These uncertainties are not flaws but essential parts of the scientific process. Honest acknowledgements that measurements are never perfect, that nature does not yield her secrets without ambiguity. Yet, despite uncertainties, the data converge on a clear picture. Webb has found numerous galaxies at redshifts above 10, many with masses exceeding 10 billion solar masses, showing active star formation and chemical enrichment existing when the universe was less than 500 million years old. These are not marginal detections or controversial interpretations. They are robust measurements, confirmed across multiple studies by independent teams. The numbers tell a story that contradicts expectations, and that story cannot be dismissed. Galaxies are built from stars, and stars take time to form, to live, to die. This basic truth has shaped our understanding of cosmic history. The earliest stars, those first-generation objects born from primordial hydrogen and helium, should have been massive, short-lived, and rare. Their deaths would have seeded space with heavy elements, enabling the next generation to form with richer chemistry. This cycle of birth and death, of chemical enrichment accumulating over time, should have unfolded gradually across hundreds of millions of years. Webb's discoveries suggest it happened far faster than anyone predicted. The deeper mystery is not just that galaxies appeared early, but that they contained stars that seemed impossibly mature. When astronomers analysed the spectra of Webb's early galaxies, they found evidence of chemical enrichment, the presence of elements like oxygen, carbon, and iron that could only come from stellar nucleosynthesis. These elements form in the cores of massive stars and are dispersed into space when those stars explode as supernovae. Finding them in galaxies less than 500 million years after the Big Bang means that at least one generation of stars had already completed its life cycle. The timeline becomes uncomfortably tight. A massive star, perhaps 50 or 100 times the Sun's mass, might live only a few million years before exploding. That is fast by stellar standards, but still requires time. The star must first form from a collapsing gas cloud, a process that itself takes time as turbulence and magnetic fields resist gravity's pull. Then it must burn through its nuclear fuel, fusing hydrogen into helium, helium into carbon and oxygen, and so on up the periodic table until it reaches iron and can go no further. Only then does it explode, scattering newly forged elements into the surrounding medium. For Webb's galaxies to show chemical enrichment at redshifts of 10 or 12, this entire process must have happened even earlier, perhaps when the universe was just 200 to 300 million years old. That leaves very little margin. It means the first stars must have formed almost immediately after the cosmic dark ages ended, perhaps even before they fully ended, igniting as soon as conditions allowed and rapidly progressing through their life cycles. The evidence comes from spectral lines. Oxygen emits characteristic light at specific wavelengths when energized by hot young stars. The strength of these oxygen lines in Webb's early galaxies indicates substantial oxygen abundance, sometimes 10 to 20% of the levels found in the Sun. Since oxygen is primarily produced in massive stars and dispersed through supernovae, its presence implies that many massive stars had already exploded. The sheer quantity suggests not just a handful of early stars, but entire populations, enough to significantly enrich the gas from which later stars would form. Some galaxies show evidence of multiple stellar populations, stars of different ages coexisting within the same system. This is inferred from the combination of spectral features. Emission lines indicate ongoing star formation, young hot stars ionizing surrounding gas. But absorption features in the continuum, subtle dips at specific wavelengths, suggest older stars are also present, stars that have settled into cooler, longer-lived phases. The coexistence of young and old populations means star formation in these galaxies was not a single burst but an extended process, or perhaps multiple episodes separated by quieter periods. This raises the question of how such complexity could emerge so quickly. In the modern universe, galaxies build their stellar populations over billions of years through episodic star formation. Bursts of activity alternate with quiet phases as gas reservoirs are depleted and then replenished by inflows or mergers. To compress that complexity into the first few 100 million years requires either much faster cycles or entirely different mechanisms. One possibility is that star formation efficiency was far higher in the early universe. Perhaps the dense gas conditions, the lack of metals that would normally cool and fragment gas, clouds, or the absence of disruptive feedback allowed stars to form rapidly once conditions were right. If gas could convert to stars at near maximum rates, then large stellar populations could accumulate quickly. Another possibility involves the nature of the first stars themselves. If those initial objects were predominantly very massive, in the range of 100 to 300 solar masses, they would have been extraordinarily luminous and short-lived, racing through their life cycles in just a few million years. They would have enriched their surroundings rapidly, but they also would have been rare and difficult to form, requiring special conditions. Finding evidence of their influence so widely spread across Webb's early galaxies suggests that either they were more common than expected, or that enrichment mechanisms were more efficient. There is also the intriguing possibility that some stars in these early galaxies are genuinely old, meaning they formed even before the observed galaxies assembled. Perhaps the first stars formed in isolation or in small groups, enriched their local environments, and then were later gathered into larger structures as gravity pulled matter together. In this scenario, the galaxies Webb sees would be aggregations of pre-existing stellar populations rather than sites of fresh star formation. This would push the timeline even further back, requiring stars to have formed when the universe was just 100 to 200 million years old. The deeper mystery extends to the question of how quickly chemical evolution proceeded. In our own Milky Way, It took billions of years for oxygen and iron abundances to reach current solar values. The galaxy built up its chemical inventory gradually through countless generations of stars. Webb's early galaxies appear to have achieved significant enrichment in a tiny fraction of that time. Either the enrichment process was fundamentally different, perhaps driven by an initial burst of massive stars that polluted the gas immediately, or our understanding of how metals are produced and dispersed needs revision. Some researchers have suggested that the first supernova explosions might have been more efficient at mixing enriched material throughout their host galaxies. In the dense environments of early structures, with less volume to fill, metals might have spread quickly, reaching high abundances with fewer stellar generations. Others propose that early galaxies might have experienced rapid inflows of enriched gas from surrounding regions, inheriting metals produced elsewhere rather than manufacturing them all internally. The stars that live too soon remain one of Webb's most profound puzzles. They force us to reconsider not just when galaxies formed, but how quickly stellar evolution proceeded, how efficiently stars produced and dispersed heavy elements, and whether the earliest phases of star formation followed rules different from those we observe today. If finding mature galaxies in the early universe was surprising, discovering massive black holes at those same epochs was shocking. Black holes are gravity's ultimate expression, regions where matter has collapsed so completely that nothing, not even light, can escape. They grow by consuming gas, dust, and stars, or by merging with other black holes. Both processes take time. Yet Webb has revealed black holes weighing millions or even billions of times the Sun's mass existing when the universe was less than 1 billion years old, a discovery that represents a turning point in our understanding of how these cosmic giants came to be. The evidence for these early black holes comes primarily from quasars, galaxies with extraordinarily luminous centers powered by material spiraling into supermassive black holes. As gas falls toward the black hole, it forms an accretion disk, a swirling maelstrom heated to millions of degrees by friction and compression. This superheated material radiates across the electromagnetic spectrum, sometimes outshining the entire galaxy of stars surrounding it. Quasars have been known since the 1960s, but Webb has pushed their detection into earlier epochs, finding them at redshifts exceeding 10. These early quasars imply black holes of staggering mass. To shine as brightly as observed, even accounting for the dimming effect of cosmic distance, the central black holes must weigh at least millions of solar masses. Some candidates suggest masses approaching 1 billion suns. The puzzle is how such massive objects could exist so early. Black holes typically form from the deaths of massive stars. When a star many times the Sun's mass exhausts its nuclear fuel, its core collapses, and if massive enough, it forms a black hole weighing perhaps 10 to 100 solar masses. This stellar remnant can then grow by accreting material from its surroundings. Gas falling in adds mass slowly, limited by radiation pressure that pushes against the inflow. Mergers with other black holes provide occasional growth spurts. Over billions of years, these processes can build supermassive black holes, but Webb's black holes exist less than 1 billion years after the Big Bang. Even if they started from stellar remnants weighing 100 solar masses immediately after the first stars formed, growing to 1 million or billion solar masses in the available time requires continuous feeding at or above theoretical limits. This limit, called the Eddington rate, is set by the balance between gravity pulling matter in and radiation pushing it out. Exceeding this rate is possible, but requires special conditions. Theorists have proposed several mechanisms for rapid black hole growth. One is super Eddington accretion, where black holes feed on dense gas clouds so quickly that radiation cannot halt the inflow. Another is the direct collapse scenario, where massive clouds of primordial gas collapse directly into black holes without first forming, two stars. creating seeds weighing tens of thousands of solar masses that can then grow to supermassive status more quickly. Yet another possibility involves primordial black holes, hypothetical objects formed in the first moments after the Big Bang, from density fluctuations in the early universe. If such black holes existed with masses ranging from hundreds to millions of solar masses, they could serve as ready-made seeds for the supermassive black holes, Webb observes. This idea has the advantage of bypassing the formation bottleneck entirely, but it requires exotic physics in the very early universe and lacks direct evidence. Webb's observations have added urgency to these debates. The telescope has not only found distant quasars, but also studied their properties in detail. Spectra reveal the black hole's masses through the motion of surrounding gas, measured via the Doppler broadening of emission lines. They also show the chemical composition of material feeding the black holes, providing clues about the stellar populations in the host galaxies. Some of these early black holes appear to be growing in tandem with their host galaxies, a relationship seen in the modern universe, where black hole mass correlates with the mass of the galactic bulge. This coevolution suggests that black holes and galaxies influence each other's growth through feedback processes. Radiation and winds from the accreting black hole can heat or expel gas, regulating star formation. Conversely, galaxy mergers can funnel gas toward the center, feeding the black hole. If this coevolution was already established in the first billion years, it implies a level of coordination and interplay that developed remarkably quickly. The turning point Webb represents is the recognition that black holes are not latecomers to cosmic history, but early players. They were present and influential when galaxies were first assembling, shaping the evolution of those galaxies through their energetic feedback. This shifts the narrative from a bottom-up story, where galaxies form first and black holes follow, to a more intertwined tale where both emerge together, each affecting the other from the start. The discovery also connects to the broader mystery of early structure formation. If black holes could grow so quickly, what does that say about the conditions in the early universe? Perhaps gas was denser, more readily available for accretion. Perhaps dark matter halos collapsed earlier and more deeply, creating environments where both stars and black holes could form in abundance. Perhaps the turbulent conditions of the young cosmos, with frequent mergers and violent dynamics, accelerated growth processes that would be slower in the calmer modern universe. There is also the question of how common these early black holes are. Quasars are the brightest examples, visible across the universe because of their luminosity. But for every shining quasar, there might be many more black holes accreting, quietly, too faint to detect at such distances. If true, then supermassive black holes might have been widespread in the early universe, present in most large galaxies even if not always actively feeding and glowing. Webb continues to search for these objects, targeting regions of sky where theory predicts they might hide, using its infrared sensitivity to pierce through the dust that often surrounds accreting black holes. Each new detection refines our understanding, narrowing the range of possible formation mechanisms, testing whether the universe's earliest black holes followed rules we can explain, or whether they demand new physics. The black holes at the beginning mark a turning point not just in knowledge but in perspective. They remind us that the universe's infancy was not a gentle awakening but a violent, energetic era where extremes were the norm, where structures we associate with maturity were already present, already shaping the cosmos in ways we are only now beginning to comprehend. When a telescope reveals something genuinely new, the consequences ripple outward far beyond academic papers and conference presentations. They reach into classrooms, into textbooks, into the fundamental narratives we tell about the universe's history. Webb's discoveries have triggered exactly this kind of ripple, forcing educators, writers, and scientists to reconsider how we teach cosmology, how we explain the early universe, and what we tell the next generation about when and how the first structures formed. For decades, cosmology textbooks presented a clear timeline. The Big Bang occurred 13.8 billion years ago. For the first few 100,000 years, the universe was opaque, filled with hot plasma. Then atoms formed, light was released, and the cosmic microwave background marked this moment of transparency. A period of darkness followed, lasting perhaps 200 to 400 million years, during which no stars yet burned. Gradually, the first stars ignited, small proto-galaxies assembled, and over the next billion years, these fragments merged into recognizable galaxies. This narrative was neat, supported by theory and observation, and taught to students worldwide. Webb has shown that this narrative was incomplete. The darkness did not last as long as expected. Galaxies did not assemble slowly. The first billion years were not a period of gradual construction, but an era of rapid, perhaps explosive development. Textbooks that once described early galaxies as small and irregular must now acknowledge that some were large and structured. Chapters explaining that supermassive black holes took billions of years to form must now include caveats about early massive black holes appearing much sooner. The timeline itself, that carefully calibrated sequence of epochs, requires revision. This rewriting has already begun. New editions of cosmology textbooks published since Webb's launch include sections on the telescope's findings, on the tension between observation and theory, on the questions now demanding answers. Some authors add cautionary notes, reminding readers that the field is in flux, that interpretations may change as more data arrive. Others embrace the uncertainty, presenting it as an opportunity to witness science in action, to see how knowledge evolves when confronted with unexpected evidence. The consequences extend beyond printed pages. University courses on cosmology have been updated, lectures revised to incorporate Webb's discoveries. Professors who spent years teaching the standard model now find themselves explaining why that model might need modification. Some frame this as a crisis, a moment when established ideas face serious challenge. Others present it as normal scientific progress, the natural outcome of building better instruments and looking deeper into the cosmos. For students, particularly those just entering the field, Webb's discoveries are both exciting and destabilizing. Exciting because they offer a chance to contribute to resolving genuine mysteries, to work on questions where the answers are not yet known. Destabilizing because the foundations seem less solid than previous generations enjoyed. Students learning cosmology today must hold multiple possibilities in mind simultaneously, understanding both the standard model and its potential alternatives, both the old timeline and the emerging revisions. The rewriting also affects public understanding. Documentaries, planetarium shows, and science communication efforts must now convey not just the beauty of Webb's images, but the deeper implications. Explaining to a general audience that galaxies appeared earlier than expected requires first explaining what was expected and why. It requires acknowledging uncertainty, admitting that scientists do not have all the answers, while still conveying the progress being made. This balance between honesty about unknowns and confidence in the scientific process is delicate but essential. Some educators have embraced Webb's discoveries as teaching moments, opportunities to illustrate how science works. They show students the timeline before Webb, present the observations that contradicted it, and discuss the various theories proposed to explain the discrepancies. This approach demystifies science, revealing it not as a collection of fixed facts, but as an ongoing investigation, a conversation between theory and observation where both sides must be willing to adjust. The consequences also reach into adjacent fields. Theories of star formation, once developed to explain nearby stellar nurseries, must now account for the apparently more efficient processes operating in the early universe. Models of dark matter clustering, calibrated against observations of galaxy distributions, face pressure to explain why early structures assembled faster than predicted. Even studies of exoplanets and the potential for life are affected, because if heavy elements appeared earlier than expected, rocky planets could have formed sooner, potentially extending the window for biological evolution. There is resistance to some of the rewriting, not from stubbornness, but from caution. Scientists who devoted careers to building the standard model understandably hesitate before abandoning it. They point out that Webb is still new, that not all observations have been fully vetted, that alternative explanations might yet reconcile the data with existing theory. This caution is healthy, preventing premature conclusions, but it also creates tension between those eager to embrace new paradigms and those defending established frameworks. The rewriting is not uniform across all levels of education. Elementary school presentations about the universe might mention Webb without delving into the complications it introduces. High school textbooks might acknowledge the discoveries but avoid the technical details. University-level courses and graduate seminars engage with the full complexity, weighing different interpretations and exploring the mathematical models underlying each. This stratification reflects the challenge of communicating cutting-edge science across audiences with vastly different backgrounds. Museums and science centres face their own version of this challenge. Exhibits designed years ago to explain galaxy formation may now seem outdated, their timelines too cautious, their narratives too simple. Some institutions have added supplementary displays about Webb, acknowledging the new discoveries while leaving older exhibits in place. Others are planning comprehensive updates, redesigning entire sections to reflect current understanding or lack thereof. The consequence of Webb's discoveries is thus not a single rewritten textbook, but a cascading series of revisions across education, communication, and public understanding. It is a reminder that scientific knowledge is always provisional, always subject to revision in light of new evidence. And while this might seem unsettling, it is also the source of science's strength, its ability to correct itself, to grow, to move closer to truth even when that means acknowledging past mistakes. The textbooks will continue to be rewritten as Webb's mission progresses, as more data accumulate, as theories are tested and refined. Each revision will bring us closer to an accurate account of the universe's earliest chapters, even if that account turns out more complex and surprising than anyone anticipated. Scientific discoveries rarely remain confined to their original domains. They echo outward, influencing fields that might seem unrelated, changing how researchers in distant specialties think about their own problems. Webb's revelations about the early universe have sent such echoes rippling through multiple branches of science, from particle physics to astrobiology, from philosophy to technology, reshaping questions and opening new avenues of investigation. In particle physics, Webb's discoveries have renewed interest in the nature of dark matter. If galaxies formed earlier than the standard cold dark matter model predicts, then perhaps dark matter's properties differ from assumptions. Particle physicists who search for dark matter candidates in underground detectors or particle accelerators now have additional motivation to explore alternatives. Warm dark matter, self-interacting dark matter, or even more exotic possibilities become worth investigating, not just as theoretical curiosities, but as potential solutions to observational puzzles. Webb has given particle physics new targets, new reasons to question whether the simplest dark matter models are sufficient. Cosmologists working on inflation, that brief period of exponential expansion thought to have occurred fractions of a second after the Big Bang, also feel Webb's impact. Inflation is invoked to explain why the universe is so uniform on large scales and why it has the geometry we observe. Different inflation models make different predictions about the density fluctuations that seed galaxy formation. If Webb shows that galaxies assembled faster than expected, it might favour inflation models that produce larger or more varied fluctuations. This connection between the universe's first moments and its first galaxies provides a rare observational link between two epochs separated by hundreds of millions of years. Astrobiology, the study of life beyond Earth, faces intriguing implications. If heavy elements appeared earlier than expected, dispersed by the first generations of stars, then rocky planets could have formed sooner. The building blocks of life, carbon, nitrogen, oxygen, phosphorus, forged in stellar cores and scattered through space, would have been available earlier in cosmic history. This potentially extends the timeline for the emergence of life, raising the possibility that biological processes began not just billions of years ago, but perhaps many billions, in galaxies and on worlds that have long since evolved or disappeared. Webb's discoveries do not prove life exists elsewhere, but they expand the window of opportunity. Philosophers of science find rich material in Webb's impact. The tension between theory and observation, the challenge of revising established paradigms, the way scientific communities negotiate consensus when faced with anomalies, all these are themes philosophers have explored for decades. Webb provides a contemporary case study, a real-time example of science grappling with unexpected evidence. Questions about scientific realism, about whether our theories describe reality or merely organize observations, become more than abstract debates when a telescope shows us galaxies that do not fit our best models. Technology development also feels the echo. Webb itself is a triumph of engineering, pushing the boundaries of mirror fabrication, cryogenic systems, and precision pointing. The problems solved to make Webb work have applications beyond astronomy. The techniques developed for aligning its segmented mirror might inform next-generation space telescopes or even Earth-based instruments. The materials designed to withstand extreme temperature gradients could find use in other aerospace applications, and the data processing algorithms created to extract faint signals from noisy images have potential uses in medical imaging, surveillance, or artificial intelligence. The impact extends to how we think about time and history. Webb allows us to see the universe not as it is, but as it was, billions of years in the past. This shifts our temporal perspective, making ancient history immediate and accessible. We become witnesses to events that occurred before our solar system formed, observers of a cosmic past that shaped the present. This unusual relationship with time, mediated through light and telescopes, challenges intuitions about causality and sequence, reminding us that the universe's timeline is not a simple line but a complex web, where past and present coexist in the light, reaching us now. Education in STEM fields has been energized by Webb's discoveries. Students see that fundamental questions remain unanswered, that science is not a completed edifice, but a growing structure with frontiers still open. This can inspire young researchers to pursue careers in astronomy, physics, or engineering, knowing that their contributions could help solve real mysteries. The excitement generated by Webb's images and findings serves as a recruiting tool for science, drawing in minds that might otherwise have chosen different paths. International collaboration, already strong in astronomy, has been reinforced by Webb's mission. The telescope is a joint project involving NASA, the European Space Agency, and the Canadian Space Agency, with scientists from dozens of countries contributing to observations and analysis. Webb's discoveries belong to humanity as a whole, and the collaborative model demonstrates what can be achieved when nations pool resources and expertise. This model may influence future large-scale scientific projects, showing that cooperation yields results beyond what any single nation could accomplish alone. The impact also reaches popular culture. Webb's images have appeared in art installations, inspired musical compositions, and featured in literature. The telescope has become a symbol of human curiosity and achievement, a modern monument to our desire to understand the cosmos. This cultural resonance matters because it shapes how societies value science, how willing they are to fund research, and how they incorporate scientific perspectives into broader conversations about meaning and existence. Even economics feels a subtle influence. The technologies developed for Webb, from advanced optics to sophisticated sensors, have commercial potential. Companies involved in the telescope's construction have gained expertise that can be applied to other ventures. The inspiration Webb provides might motivate students to pursue technical careers, eventually contributing to innovation and economic growth. While these economic impacts are difficult to quantify, they represent another way the telescope's discoveries echo through society. Webb's impact is thus not confined to astronomy. It spreads through science and beyond, touching fields and endeavours that might seem distant from observing distant galaxies. This is the nature of fundamental discovery. When we learn something genuinely new about the universe, the knowledge does not stay isolated. It connects, influences, and transforms, sending echoes that can be heard far from where the original sound was made. Behind every telescope, every image, every discovery, there are people, human beings with hopes and fears, with dedication spanning decades, with skills honed through years of training. The James Webb Space Telescope exists not because of inevitable technological progress, but because thousands of individuals chose to devote significant portions of their lives to making it real. Their stories, often overlooked in favour of the scientific results, are themselves worth telling. The dream of Webb began in the late 1980s and early 1990s, when astronomers recognised that Hubble, magnificent as it was, would eventually need a successor. A handful of visionaries imagined a telescope optimised for infrared, capable of seeing the first galaxies, studying exoplanet atmospheres, and probing regions hidden from visible light. These early advocates wrote proposals, gave presentations, built coalitions of support among scientists and funding agencies. Without their persistence, Webb would never have moved from concept to reality. Among them was John Mather, a Nobel Prize-winning astrophysicist who became one of Webb's senior project scientists. Mather had worked on the Cosmic Background Explorer satellite, which measured the microwave background with unprecedented precision. He understood both the science Webb could accomplish and the technical challenges it would face. For more than 2 decades, he championed the mission, navigating bureaucratic obstacles, budget crises, and technical setbacks. His commitment, along with that of other senior scientists, provided stability and vision even when the project seemed in danger of cancellation. Engineers formed the backbone of Webb's development. Thousands worked on different aspects: the mirrors, the sunshield, the instruments, the spacecraft bus. Each component demanded innovation. The primary mirror, composed of 18 beryllium segments coated in gold, required new fabrication techniques. Engineers had to design actuators that could adjust each segment's position to nanometer precision in the cold of space. The sunshield, with its 5 layers of Kapton film, each barely thicker than a human hair, had to deploy reliably despite never being fully tested on Earth in the far conditions it would face in space. These engineers spent years solving problems that had no precedent. How do you fold a tennis court-sized sunshield so it fits in a rocket, then unfold it flawlessly in zero gravity? How do you keep instruments cold enough to detect faint infrared signals while electronics generate heat? How do you align mirrors separated by meters when thermal expansion and contraction constantly shift their positions? Each question demanded not just technical knowledge, but creativity, persistence, and a willingness to test ideas that might fail. The technicians who assembled Webb, working in clean rooms with tools designed for precision, also played crucial roles. They polished mirrors, tested components, integrated systems, each step documented and verified. A single mistake, a particle of dust, a misaligned connector, could have doomed the mission. The responsibility they carried was immense, yet they performed their work with meticulous care, knowing that Countless others depended on their precision. There were project managers who kept the sprawling effort coordinated, ensuring that teams working on different continents stayed synchronized, that schedules were met or adjusted when necessary, that budgets stretched to cover unexpected challenges. These managers often worked in obscurity, their contributions invisible in the final product, yet essential to making that product possible. Young scientists, graduate students and postdocs contributed their energy and ideas. Many spent years developing the science cases for Webb observations, planning what the telescope should look at and why. They wrote proposals competing for precious observing time, knowing that only a fraction would be accepted. Some of these young researchers have now built careers around Webb data, analyzing spectra, interpreting images, writing papers that push forward our understanding. For them, Webb represents not just a telescope, but a defining opportunity, a chance to work on questions that genuinely matter. There were moments of crisis that tested everyone's resolve. Technical problems emerged during development that seemed insurmountable. Costs escalated beyond original estimates, leading to congressional hearings and threats of cancellation. Delays pushed the launch date years into the future, frustrating scientists who had planned careers around Webb's anticipated timeline. Through each crisis, the people behind Webb made difficult choices, redesigned components, defended the mission's value, and kept moving forward. The launch itself, on December 25th, 2021, was an emotional culmination. Engineers and scientists who had worked on Webb for decades gathered to watch the Ariane rocket lift off from French Guiana. The tension was palpable. So much could still go wrong. The rocket could fail. The deployment sequence, with its hundreds of steps, could encounter an error. Years of work could be lost in moments. When the rocket successfully placed Webb on its trajectory toward the second Lagrange point, there was relief but also awareness that the hardest part lay ahead. The deployment period, those 29 days when Webb unfurled in space, transformed anxiety into cautious optimism. Each successful step, the sunshield unfurling, the mirrors swinging into position, the instruments coming online, brought celebration tempered by the knowledge that more steps remained. When the first test images arrived, showing stars in perfect focus, engineers and scientists wept openly. The telescope worked. The years of effort had succeeded. Now, as Webb sends back data that challenges our understanding of the universe, the people behind it watch with a mixture of pride and wonder. They built a tool that exceeded expectations, that revealed things no one predicted, that opened new frontiers. Their names may not appear in headlines, but their contributions are embedded in every image, every spectrum, every discovery. The human element of Webb is a reminder that science is not done by institutions or instruments, but by people. People who dream of understanding the cosmos, who spend careers solving problems, who persist through failure and setback, who collaborate across borders and disciplines, who find meaning in pushing the boundaries of knowledge. The telescope is their monument, but more than that, it is their gift to humanity, a tool for seeing farther, understanding deeper, and appreciating more fully the universe we inhabit. Not everyone greets Webb's discoveries with enthusiasm for revolution. Within the scientific community, a significant contingent defends the standard cosmological model, arguing that the anomalies, while real, do not require abandoning the framework that has served so well for decades. These scientists are not deniers or obstructionists, but careful thinkers who understand that extraordinary claims require extraordinary evidence, and that the evidence from Webb, while suggestive, may not yet be conclusive enough to justify radical revision. Their position rests on several arguments. First, they point out that Webb is still early in its mission. The telescope has been collecting data for a limited time, focusing on specific targets that may not represent the universe as a whole. Early massive galaxies might be rare exceptions rather than common objects. observational biases could be at play. Webb naturally finds the brightest, most massive galaxies because those are easiest to detect at extreme distances. Fainter, more typical galaxies might remain below the detection threshold, giving us a skewed view of the early universe. If most early galaxies match predictions and only a few outliers appear anomalous, then the standard model might survive intact. Second, defenders of the standard model emphasize uncertainties in measurements. Estimating galaxy masses from their light requires assumptions about stellar populations, dust content, and star formation histories. Different assumptions yield different mass estimates. If masses are systematically overestimated due to incorrect assumptions, then the apparent tension with models might disappear. Some researchers have reanalyzed Webb's data using alternative methods and found somewhat lower masses, enough to ease but not eliminate the discrepancy. They argue that as techniques improve and more data accumulate, the anomalies might shrink. Third, there is the argument that models can be adjusted within the standard framework. The standard cosmological model, lambda CDM, is remarkably flexible. It includes parameters that can be tuned to match observations. If star formation efficiency was higher in the early universe, that can be incorporated without abandoning the model's foundation. If feedback processes were weaker, that too can be adjusted. Defenders argue that what appears as a crisis is actually the normal process of refinement, where observations push models to evolve, but do not require revolution. They point to history as support. Throughout the development of modern cosmology, observations have repeatedly challenged prevailing ideas, yet the core framework has adapted and survived. When the universe's expansion was discovered to be accelerating, dark energy was introduced to explain it. When galaxy rotation curves did not match visible matter, dark matter was proposed. When the microwave background showed temperature fluctuations, inflation was added to account for them. Each time, the model grew more complex but remained fundamentally intact. Defenders believe Webb's discoveries represent another such moment, where adjustments rather than abandonment are required. Some critics of the revolutionary interpretations focus on the specific mechanisms proposed to explain early massive galaxies. They argue that exotic ideas like primordial black holes or cyclic universes lack supporting evidence beyond their ability to explain one puzzle. Science should prefer the simplest explanation consistent with data, a principle known as Occam's razor. If adjustments to star formation efficiency or dark matter behavior can explain Webb's observations without invoking entirely new physics, those adjustments should be preferred. There is also concern about premature conclusions affecting public perception of science. Defenders worry that proclaiming the Big Bang wrong, or cosmology in crisis, as some headlines have done, undermines confidence in scientific knowledge. They fear that if every new observation is framed as overturning established understanding, the public will see science as unreliable, constantly changing its mind. They prefer a more measured message that Webb has revealed interesting anomalies being actively investigated without declaring the entire cosmological framework obsolete. The opposition also includes those who question specific interpretations of Webb's data. Some researchers have proposed that what appear as massive galaxies might actually be smaller systems experiencing brief but intense starbursts, making them appear brighter and more massive than they truly are. Others suggest that active galactic nuclei, luminous black holes, could be contributing significant light, inflating estimates of stellar mass. If these alternative explanations hold, then the galaxies might not be as anomalous as initially thought. Debates between revolutionary and conservative camps play out in academic journals, at conferences, and in online forums. Papers proposing new physics are met with responses questioning their assumptions. Simulations claiming to reproduce Webb's observations are critiqued for the parameters chosen or the simplifications made. This back and forth is healthy. The scientific process at work, where ideas are tested through argument and evidence rather than authority or consensus. Some defenders acknowledge that revisions may be necessary, but urge caution about their extent. They accept that the early universe might have been more active than previously thought, that galaxies formed somewhat faster, that black holes grew more efficiently, but they resist the idea that the entire timeline or the fundamental physics needs changing. They see Webb's discoveries as important refinements rather than fundamental challenges, adjustments to details rather than rewrites of the story. There is also philosophical opposition to abandoning successful theories lightly. The Standard Model has made testable predictions that were confirmed, from the existence of the microwave background to the abundance of light elements to the large-scale structure of the universe. A theory with such a track record deserves respect and should not be discarded without compelling reason. Defenders argue that Webb has raised questions but not provided definitive answers, and that patience is warranted as more observations accumulate. The opposition serves an important function. It acts as a brake-on, runaway speculation, ensuring that new ideas are rigorously tested before being accepted. It demands that revolutionary claims meet high standards of evidence, and it reminds the community that the Standard Model, for all its potential shortcomings, remains the best description we have until something demonstrably better replaces it. As Webb's mission continues, the tension between revolutionary and conservative interpretations will likely persist. Both sides will gather evidence, refine arguments, and test predictions. Eventually, one view will gain stronger support, or perhaps a synthesis will emerge that incorporates elements of both. But for now, the opposition to radical revision remains a vibrant and necessary part of the scientific conversation Webb has sparked. There comes a moment in every profound discovery when understanding shifts, when the accumulation of evidence crosses a threshold and we see the cosmos differently than before. For many researchers working with Webb's data, that moment has arrived. Not a sudden revelation, but a gradual awakening to the realization that the universe is more complex, more inventive, and more surprising than the neat models suggested. This awakening is not about admitting failure, but about embracing a richer, more nuanced picture of cosmic history. The complexity reveals itself in layers. At the surface, Webb shows galaxies where models predicted none, or at least none so large. Dig deeper, and you find that these galaxies have diverse properties, some actively forming stars, others showing signs of quiescence, some chemically enriched, others more pristine. The diversity itself is telling. The early universe was not uniform, not proceeding through a single path of evolution, but exploring multiple pathways simultaneously, different environments producing different outcomes even within the same cosmic epoch. This diversity extends to star formation. Some early galaxies show spectral signatures of intense starbursts, regions where stars are being born at prodigious rates, perhaps triggered by gas-rich mergers or unstable disks. Others display calmer signatures, suggesting steady but less dramatic star formation. Still others show evidence of recent quenching, where star formation has suddenly ceased, perhaps due to feedback from supernovae or active black holes. That such variety exists so early indicates that the physical processes shaping galaxies were already diverse, already operating in different modes depending on local conditions. The presence of massive black holes adds another layer of complexity. These are not passive objects, but active participants in galaxy evolution, regulating star formation through their energetic feedback, accreting matter and growing in mass, perhaps even triggering star formation in some circumstances while suppressing it in others. The interplay between black holes and their host galaxies appears to have been established remarkably early, suggesting a evolution that is more intricate and fundamental than previously appreciated. Dark matter's role also appears more complex. While the Standard Model treats dark matter as a simple, non-interacting substance that clumps under gravity, Webb's observations hint at richer behavior. The early formation of massive structures might require dark matter halos that collapsed more quickly or more deeply than simulations predict. Perhaps dark matter's distribution was lumpier, with rare high-density peaks where galaxies could form faster. Perhaps interactions between dark matter particles, weak but non-zero, affected how halos assembled. Each possibility adds complexity to a picture that was once straightforward. The chemical evolution of the early universe shows similar complexity. Different galaxies exhibit different metallicities, different ratios of elements, suggesting varied star formation histories and supernova rates. Some appear to have experienced rapid enrichment from a first generation of massive stars. Others show more gradual chemical evolution. The scatter in properties indicates that the early universe was not a monolithic environment, but a patchwork of different conditions, each producing galaxies with unique characteristics. There is also temporal complexity. The early universe was not a static tableau, but a dynamic era with rapid changes. Galaxies formed, merged, grew, and sometimes quenched on timescales of tens to hundreds of millions of years. The first billion years, which once seemed like a slow prelude to later activity, now appears as a period of frantic construction, deconstruction, and reconstruction. Structures assembled quickly, sometimes fell apart, and reassembled in new configurations. This dynamism contrasts with the stately evolution of the modern universe, where processes unfold over billions of years. Recognizing this complexity requires a shift in how we think about cosmic history. Instead of a linear progression from simple to complex, we see a universe that was complex from near the beginning, exploring possibilities, testing configurations, with some pathways proving more successful than others. Instead of a single timeline, we see multiple timelines running in parallel, different regions evolving at different rates depending on their local conditions. This awakening to complexity is intellectually humbling but also exhilarating. It means the universe is not a solved problem but an ongoing mystery. It means there are patterns and processes we have not yet identified, relationships we have not yet understood. Every new layer of complexity is an invitation to look deeper, to think more carefully, to develop more sophisticated models that capture the richness of reality. For scientists, this awakening changes priorities. Research that once focused on refining parameters within the standard model now explores alternative frameworks. Simulations become more detailed, incorporating physics that was previously neglected or simplified. Observers design surveys to capture the full diversity of early galaxies rather than focusing only on the most extreme examples. Theorists collaborate more closely with observers, ensuring that models are tested against the full range of data rather than cherry-picked examples. The complexity also affects how discoveries are communicated. It is no longer sufficient to say Webb found massive early galaxies. The statement must be qualified with recognition of the diversity, the uncertainties, the multiple interpretations. This makes communication harder but more honest, acknowledging that science rarely provides simple answers to complex questions. There is a parallel to how we understand life on Earth. Early biology imagined evolution as a ladder of progress, with simple organisms gradually becoming more complex. Modern biology recognizes evolution as a branching bush, with complexity emerging, disappearing, and re-emerging along countless pathways. The universe's evolution may be similar, not a ladder but a bush, with many branches exploring different possibilities, some leading to familiar structures, others to configurations we are only beginning to discover. The awakening to complexity is ongoing. Each new Webb observation adds detail, reveals new facets, poses new questions. The picture that emerges is not simpler than before, but richer, more textured, more fascinating. It is a universe that refuses to be reduced to simple formulas, that demands we engage with its full intricacy if we hope to understand it. And perhaps this is as it should be. A universe simple enough to fully understand might be less interesting than one that constantly surprises us, that rewards curiosity with deeper mysteries, that awakens us to the realization that complexity is not an obstacle to knowledge, but its very essence. Of all the possibilities Webb's discoveries raise, one stands out as most profound and most unsettling. What if the timeline itself is wrong? Not just the details of when galaxies formed or how quickly stars evolved, but the fundamental age of the universe, the number we have spoken with such confidence, 13.8 billion years. What if that figure, derived from our best measurements and most successful theories, is off by enough to matter? This is the deepest revelation Webb forces us to consider, and it cuts to the heart of how we understand cosmic history. The age of the universe is not a direct measurement, but a calculation based on the expansion rate and the composition of the cosmos. We measure how fast galaxies are receding. We account for the density of matter and dark energy. We work backward using Einstein's equations of general relativity. And we arrive at an age. The cosmic microwave background provides an independent check, its detailed patterns encoding information about the universe's age when that light was released. The two methods agree remarkably well, both pointing to 13.8 billion years, give or take 100 million. But what if subtle errors have crept into these calculations? What if the expansion rate is not quite constant in the way we assume? What if dark energy behaves differently at early times than it does today? What if our understanding of gravity at cosmological scales contains small inaccuracies? Any of these could shift the calculated age, potentially making the universe older than we think. An older universe would solve many of Webb's puzzles. If the universe is 14 or 15 billion years old instead of 13.8, that extra time, several 100 million years, could allow galaxies to form and grow to the masses Webb observes. Black holes would have more time to accrete material and reach supermassive status. Stars would have more time to live, die, and enrich the gas for subsequent generations. The timeline would no longer be so compressed. The anomalies would ease, and the standard model would survive with only minor adjustments. But making the universe older is not simple. It requires changing parameters in ways that affect other observations. The cosmic microwave background's patterns depend on the universe's age. Make the universe older, and those patterns should look different. Yet the microwave background matches predictions of a 13.8 billion year old universe with extraordinary precision. To change the age without breaking that agreement demands adjustments elsewhere, perhaps in the expansion history, perhaps in the balance between matter and dark energy, perhaps in subtle aspects of the physics we do not fully understand. There is another way to interpret time being wrong. Perhaps it is not the age of the universe itself, but our translation of redshift into look-back time that contains errors. Redshift tells us how much the universe has expanded since light was emitted. Converting that expansion into time requires knowing the expansion rate at every epoch, which depends on the densities of matter, dark energy, and radiation. If any of these densities were different than assumed, or if they varied in unexpected ways, the redshift to time conversion would be off. Galaxies we think existed at 500 million years might actually have existed at 700 million years, easing the tension without changing the universe's total age. Some researchers have explored whether the Hubble constant, the current expansion rate, might be different from what standard cosmology predicts. Measurements of the Hubble constant using different methods have given slightly different values, a discrepancy known as the Hubble tension. If the true value is higher than the cosmic microwave background suggests, the universe would be younger, not older, making Webb's puzzles worse. But if the resolution to the Hubble tension involves time-varying dark energy or other exotic physics, it might also affect the early universe in ways that change how we interpret Webb's observations. The possibility that time itself is wrong also raises philosophical questions. Time in cosmology is not absolute but relative, tied to the expansion of space. Different observers in different states of motion experience time differently. When we speak of the universe's age, we mean the time experienced by an observer moving with the cosmic expansion, a co-moving observer. But the universe's earliest moments were so extreme, with such high energies and densities, that the nature of time itself might have been different. Quantum effects might have made time fuzzy or discontinuous at the smallest scales. If time near the Big Bang behaved differently than time today, our extrapolation backward might not be accurate. There are speculative ideas that take this even further. Some theories propose that time did not exist before the Big Bang, that it emerged as part of the space-time structure during the initial expansion. In such frameworks, asking what happened before the Big Bang is meaningless, because there was no before. But other theories allow for time extending past what we call the Big Bang, perhaps into a previous contracting phase, or a multiverse where our universe is one bubble among many. If time has a more complex structure than we assume, then Webb's galaxies might not be as anomalous as they seem. They might fit into a longer or more intricate temporal framework. The revelation that time might be wrong is not yet proven. It remains a possibility among others, a direction some researchers are exploring while others pursue different explanations. But the mere fact that it is being seriously considered shows how deeply Webb has shaken cosmology. Time is one of the most fundamental concepts in physics, and questioning it means questioning assumptions that usually go unexamined. For those listening tonight, the idea that time itself might be uncertain can feel disorienting. We trust that the past is the past, that history unfolded in a particular sequence, that the universe's age is a fixed fact. Webb reminds us that even such basic concepts rest on measurements and models, both of which can be refined or revised. The universe's timeline is humanity's best current understanding, not an absolute truth, and understanding is always subject to change when confronted with new evidence. After journeying through data and theories, through discoveries and debates, it is worth pausing to reflect on what Webb's revelations mean not just for science but for us, for how we see ourselves in the context of this vast, surprising universe. The telescope has shown us galaxies billions of years old, structures forming at the edge of time, processes unfolding faster than expected. But beyond the technical findings lies a deeper question about meaning, about our place in a cosmos that refuses to conform to our neat expectations. Webb reminds us of our smallness. The galaxies it reveals exist at distances so vast that light takes more than 13 billion years to reach us. In that immensity, Earth is less than a speck. Our entire solar system, an insignificant dot. Our human history, a fleeting moment. We live on a planet orbiting an ordinary star in the outskirts of a galaxy that itself is just one among trillions. The scale is humbling, stripping away any illusion that we occupy a privileged position in space or time. Yet Webb also reminds us of our vastness. We are small creatures, yes, but we are creatures capable of building telescopes that can see across the universe. We can gather photons that have travelled for billions of years, and from them reconstruct the properties of galaxies born when the cosmos was young. We can measure, calculate, theorize, and understand, at least partially, the processes that shaped everything we see. That capacity for understanding, for reaching beyond our immediate surroundings and grasping the workings of the universe, is itself a kind of vastness, the richness of mind that matches the richness of the cosmos. The mysteries Webb has uncovered, the galaxies that defy explanation, the timelines that do not quite fit, these are invitations to humility. They tell us that our current understanding is incomplete, that nature is more subtle than our models capture, that the universe still holds secrets we have not imagined. This is not a failure but a gift. A universe fully understood would be a universe finished, with no more questions to ask, no more discoveries to make. The fact that Webb surprises us means we are still at the beginning of knowledge, still learning, still growing in our comprehension. There is also comfort in the universe's complexity. In our daily lives, we face uncertainties, questions without clear answers, situations that defy simple resolution. The universe is the same. It is messy, complicated, full of phenomena that do not reduce to elegant formulas. Recognizing this can ease the pressure we feel to have everything figured out. If the cosmos itself resists complete understanding, perhaps we can be gentler with ourselves when we struggle to make sense of our own smaller worlds. Webb's discoveries also connect us to time in a unique way. The light we see from distant galaxies began its journey long before humans existed, before Earth formed, before the sun ignited. That light traveled through empty space for eons, finally arriving now, just when we have built the instruments to capture it. There is something profound in this convergence, the arrival of ancient photons and the emergence of conscious beings able to appreciate them. It suggests that the universe is not indifferent to observation, that there is a deep relationship between cosmos and consciousness, even if we do not fully understand what that relationship means. Philosophically, Webb challenges notions of certainty. We build models, test them, refine them, and grow confident in their predictions. Then a new observation arrives that does not fit, and we must acknowledge that our confidence was premature. This cycle of confidence and humility is central to science, but it also applies to life. We make plans based on what we think we know, and then reality surprises us. Webb teaches that surprise is not something to fear but something to expect, part of the fabric of existence. There is also inspiration in the human achievement Webb represents. Thousands of people collaborated across decades to build a telescope that works flawlessly 1 million miles from Earth. They overcame technical challenges, budget crises, and setbacks. They persevered through doubt and delay, and they succeeded. That success is a reminder of what humans can accomplish when we work together toward a common goal. In an era often marked by division and cynicism, Webb stands as a monument to cooperation and shared purpose. The telescope also invites us to think about legacy. The discoveries being made now will shape understanding for generations. Students not yet born will learn from Webb's observations, build careers analyzing its data, formulate theories inspired by its findings. The knowledge being created is not for us alone but for those who come after, a gift passed forward through time. In this sense, Webb connects us to the future just as its observations connect us to the past. Spiritually, for those inclined towards such reflections, Webb can deepen a sense of wonder and reverence. The universe it reveals is not a cold, mechanical system, but a dynamic, creative, almost playful realm where complexity emerges, where structures form in unexpected ways, where beauty and mystery coexist. Whether one frames this in religious terms or simply as awe at nature's grandeur, the feeling is similar, a recognition that the cosmos is more than matter and energy, that it evokes something beyond the material. For the scientists working with Webb, the meaning is perhaps most personal. They have devoted years, sometimes entire careers, to this mission. Seeing their work bear fruit, revealing a universe even stranger than they hoped, brings a satisfaction that transcends professional achievement. It is the fulfillment of curiosity, the joy of discovery, the realization that their efforts have expanded human knowledge in a meaningful way. And for those of us who simply listen, who look at Webb's images and read about its findings, the meaning lies in connection. Connection to the universe's history, connection to the community of people pursuing understanding, connection to the ongoing story of humanity learning about its place in existence. Webb invites us to participate in that story, not as active researchers but as witnesses, as minds touched by wonder, as beings aware that we live in a cosmos far larger and more remarkable than we can fully grasp. As we bring this journey gently to rest, it is worth remembering that what Webb has shown us is not an ending but a beginning. The telescope continues, its observations pointing toward new regions of sky, capturing spectra of newly discovered galaxies, peering ever deeper into the cosmic past. Each observation adds detail to the picture, refines our questions, and sometimes opens entirely new mysteries. The story we have told tonight is not complete because the universe's story is still unfolding, and our understanding of it continues to evolve. Webb's mission is planned to last at least a decade, possibly longer if its systems remain healthy and its fuel supply sufficient for maintaining orbit. In that time, it will observe thousands more galaxies, study hundreds of exoplanets, map star-forming regions, and probe the earliest epochs of cosmic history. Each year will bring new discoveries, some confirming current theories, others challenging them, a few perhaps revolutionizing entire fields. The puzzles we have discussed tonight may find solutions, or they may deepen into even more profound mysteries. Webb's legacy. Ground-based observatories with enormous mirrors, space missions designed to study specific questions, new technologies we have not yet imagined, all will contribute to the ongoing effort to understand the universe. Webb is not the final word, but one chapter in a story that spans centuries, from Galileo's first telescope to instruments yet to be built. Each generation of astronomers stands on the shoulders of those before, seeing farther not because they are taller, but because they have a higher vantage point. The legacy of Webb's discoveries will be measured not just in papers published or theories revised, but in inspiration provided. Young people watching these images may decide to pursue careers in science, engineering, or technology. Teachers will use Webb's findings to illustrate how science works, how knowledge grows, how curiosity drives progress. Decades from now, when some of those inspired students have become researchers themselves, they may look back at Webb as the moment that shaped their path. There is also the legacy of what Webb represents. The idea that humanity can accomplish extraordinary things when we commit to them. The telescope required vision, persistence, collaboration, and courage. It required people willing to devote years to solving problems with no guarantee of success. It required funding agencies and governments willing to invest in knowledge for its own sake, not just for immediate practical returns. That investment has paid off not only in discoveries, but in demonstrating what is possible when we aim high. As Webb continues to operate, its data will become part of a permanent archive, accessible to anyone with the interest and skills to analyze it. Future researchers will comb through those archives, finding things the original observers missed, asking questions no one has yet thought to pose. The telescope's scientific productivity will extend far beyond its operational lifetime. Long after Webb has ceased functioning, its data will continue to yield insights, a gift that keeps giving across generations. For cosmology, the journey ahead involves reconciling Webb's observations with existing theory or developing new theories that fit better. This will not happen quickly or easily. Science does not leap from confusion to clarity in a single bound, but progresses through gradual accumulation of evidence, testing of ideas, and building of consensus. The anomalies Webb has revealed will likely take years to fully resolve, perhaps decades. But that is how deep questions are answered, through sustained effort and collective thought. The broader journey for humanity is one of continuous exploration. Webb looks outward, into space and back in time, but other instruments look inward, toward the smallest scales of matter and energy. Together, these efforts map the full range of existence, from quarks to galaxy clusters, from the first moments after the Big Bang to the far future. Each domain reveals its own mysteries, its own beauties, its own surprises. Webb is one part of this vast enterprise of understanding. There is something poignant about knowing that Webb, like all things, is temporary. The telescope will eventually run out of fuel for maintaining its orbit, or a critical system will fail and communication will cease. When that day comes, the golden mirror will fall silent, no longer gathering ancient light, no longer sending discoveries across the void. But even in silence, it will remain a monument, a testament to what we achieved in this era, floating forever in the darkness, a relic of humanity's curiosity. Yet the knowledge it provided will not fade. The images, the spectra, the measurements will be preserved, studied, and built upon. The questions it raised will continue to be asked. The inspiration it sparked will ripple forward through time. In that sense, Webb is immortal, not as a physical object, but as a contribution to the endless human quest for understanding. For you, listening tonight, as this journey draws to a close, the story does not end here. The universe Webb revealed is the same universe you inhabit, the same cosmos stretching above you when you look at the night sky. The galaxies it found, though impossibly distant, are part of the same web of structure that includes the Milky Way, the solar system, and the Earth beneath your feet. You are connected to those distant lights, made of the same elements, governed by the same laws, part of the same cosmic story. And perhaps that is the deepest meaning of Webb's discoveries. They remind us that we are not separate from the universe, but part of it. That our curiosity about distant galaxies is the universe becoming aware of itself. That our attempts to understand cosmic history are the cosmos reflecting on its own past. In seeking to know the universe, we are engaging in an act of connection, bridging the immense distances and times that separate us from the objects we study. The journey continues, for Webb, for science, for humanity, for each of us individually. The universe remains vast, mysterious, and endlessly fascinating. There will always be more to discover, more to understand, more to wonder about. And that is not a limitation but a blessing, ensuring that curiosity will never lack for questions, that wonder will never fade, that the journey of exploration will never end. Rest well tonight, knowing that above you the universe continues its ancient dance, galaxies spinning, stars burning, light travelling across the void, all of it waiting for those with eyes to see and minds to comprehend. The journey continues, and you are part of it.